Okay, a quick tutorial on one of the applications of differentiation. It's actually called comparative rates of change. And we're going to look at an example. You already have the tools necessary to handle this particular topic. It's basically the chain rule, the long form of the chain rule. Okay, so let's jump right into an example. A cube is expanding in such a way that its sides are changing at a rate of 4 cm per second. Find the rate of change of the total surface area when the volume is 216 centimeters cubed. This is actually an example problem from the text. It's on page 426. Well, let me put my spin on it. So we're given the rate at which one of the sides is increasing. I've drawn my little cube there. The rate at which the side is increasing is 4 cm per second. They want the rate at which the surface area is going to increase when the volume is 216. Well, to get the rate at which the surface area is going to increase, we have to set up a chain rule for ds dt. ds dt has to be equal to ds d something times the dx dt that they gave us. And the only thing I can put at the bottom there would be the dx as well. ds dx times dx dt. So, I already have dx dt. They gave that to me. Can I find ds dx? Well, I'll have to set up a relationship between s for surface area and x for the length of a side. The surface area for any one side of a cube would be x squared. And since there are 6 such sides, then the surface area S has to be equal to 6x squared. And if I find ds dx, then that should be 12x. Everybody should be able to differentiate that with no issues. If I plug into my chain rule, therefore, the rate at which the surface area is changing, ds dt, is equal to ds dx, which is 12x, times dx dt, which they gave me as 4. That's 12 fours, that's 48x. The units would be cm squared per second. Now, if you notice, the rate at which the surface area is changing with time, it's actually a variable rate. It depends on x. I want the rate at which the surface area is changing at the instant when the volume is 216 cm. So, the volume of the cube is given by x cubed, that's obvious. And therefore, at the point where, or at the point when the volume is equal to 216, it implies that 216 is equal to x cubed, from which I can get x. X is the cube root of 216. And I have no idea what that value is. X is equal to 216 to the power 1/3. 6, which is 6 cm. So when the volume is 216 cm cubed, the length of any one side is 6 cm. And I can plug that value of x into the expression for ds dt, the rate at which the surface area is changing. And that will be 48 times 6. And that should give me 48x times 6. 6 is 48. 6 4 is 24. 28. And that should be cm squared per second. That's a pretty straightforward problem that, as long as you can set up the appropriate chain rule, you'll be able to solve. Let's look at another example from within the exercise itself. I'm going to go to exercise 14C. And let me pick one at random. I'll pick number 9. This one says, I'll write out the question. The variables x and y are related by y is equal to 4x upon 2, 4x plus 2 upon x plus 1. Given that x and y are both functions of t, and that dy dt is 0.3, find the corresponding rate of change of x. Find rate of change of x when y is equal to 5. Okay, let's see if we can handle business here. They gave us dy dt, and they want the corresponding rate of change of x, which means they want dx dt. Can I write a chain rule for dx dt? Dx dt is dx d something. You always start with the numerator. Dx d something. You might not know at this point what it is, but it'll be times times the derivative of the function that they gave us. In this case, that would be dy dx. So this has to be dx. I'm messing this up. Dx dt is equal to all right, I'll get this. Dx dt has to be equal to has to be equal to dx dy times dy dt. There we go. Let's see if that makes sense. Dx dt, the dy will cancel with the dy, you get back the dx dt. Okay, now they gave us dy dt, so we don't have any problem with this. But how about the dx dy? Well, that's simply the reciprocal of dy dx, which means we're going to take this function that was given to us right there, and we're going to differentiate it. Y is given as 4x plus 2 over x plus 1. If we call the numerator u, I don't remember if I showed you all the short way to do this. If u is equal to 4x plus 2, and v is equal to x plus 1, du dx is equal to 4, and dv dx is equal to 1. And dy dx is equal to v du dx minus u dv dx all upon v squared. Dy dx v x plus 1 times the derivative of the numerator, which is 4, minus u 4x plus 2 times the derivative of the denominator times 1, all divided by v squared, x plus 1 all squared. Let's tidy this up a little bit more. Dy dx is equal to, opening out your brackets there, 4x plus 4, and that's minus 4x minus 2. I think I got that right. All upon x plus 1 all squared. The 4 x's will cancel out. And what's left? 4 minus 2 is 2. That looks like 2 upon x plus 1 all squared, which means the x dy has to be equal to 2 upon, has to be equal to x plus 1 all squared upon 2, the reciprocal of dy dx. Now, let's plug that into the expression we have for the chain rule right there. I write it back. Dx dt is equal to dx dy times dy dt. I just found dx dy. The expression is x plus 1 all squared upon 2. And now I got to multiply that by dy dt. They told me that that was 0.3. All right, it's a fraction. 0.3 is 3/10. So this looks like dx dt is equal to 3 into x plus 1 all squared upon 20. But they want dx dt at a specific point. They want dx dt at the point where y is 5. So when y, notice dx dt doesn't depend on y. If it had depended on y, no problem. You plug y in there and you're good to go. So we're going to write back the y function, which is given in terms of x. Y is equal to 4x plus 2. Y is equal to 4x plus 2 upon x plus 1. Double check. And when y is equal to 5, 5 is equal to 4x plus 2 upon x plus 1. If we cross multiply, we get 5x plus 5 is equal to 4x plus 2, which makes x is equal to minus 3, I think. 5x minus 4x is x. 2 minus 5 is minus 3. So when y is 5, x takes on the value minus 3. And now you can plug that value into dx dt. Dx dt will therefore be 3 into minus 3 plus 1 all squared upon 20. That's minus 2 all squared, which is 4 3's 12 over 20. 4 into 12 is 3, 4 into 20 is 5. So dx dt is 3/5. That's not too bad. Which means, okay, I know I only did 2 examples, but I want to keep this tutorial short. And I'm going to lay on the homework. You're welcome. Exercise 14C. On page 428. In the standard textbook that we're using, the Dipchan Bahal. And the numbers I want you to do, it's 1, 2, 4, 6. 1, 2, 4, 6. 7. 11 and 13. Yeah, okay, so everybody has something to do. Most of the videos I've made so far for the Unit 1 were based on finishing up the vector analysis, which I know the students in the morning group would have been finished with. So y'all didn't have anything to do, so I made this quick tutorial. So this is for everybody, of course, not just for the morning group. Both groups. All right, I'm out, and I'll just keep the videos rolling. Thank you.